Uh, let's see what we have today. We're gonna start something very actually interesting today. Procedure call. We're calling procedures and a stack. That's the hardest part of assembly. You need to know a little bit about memory, what is a stack, how we can call procedure, and yeah, that's a very low level. How we can manage memory to access, you know, um, you know, functions or procedures. We call it procedures. I don't know in other language, maybe they call it method or subroutine or function. We can have that in assembly. We're going to see how we can manage it, how we can implement that in a very low level language like assembly language. So that's what we want to talk today. So last week we mostly talk about different type of instructions in RISC-V architecture. We talked about, you learned about register type, R type. You learned, okay, R type is most of instructions that working with arithmetic and logic unit. They are R type because R type is fast. Registers are inside CPU, so it's very fast to access and run them very fast. We have some other instructions that using constant values. We call them immediate type or I type. We also talked about that. For example, when you want to add one register with some constant, you can use add I coming from an immediate part. We also talk about load store architecture. We mentioned that this computer that we are talking, that is RISC-V architecture, is a load store architecture. Load store architecture is the type of architecture that just has two instructions to access to memory. The rest are actually register based. These two instructions are load and store. However, we have different type of load and store: load word, load double word, and store same too. So we already talked about them, and you learn how to manage, these instructions, how write code to access memory and bring it inside CPU and work using those R type and return back to the memory. We had some samples, and in your midterm, probably you also encounter some of them. What else we learned? I think we also talk about branch instructions, how we can change the control flow inside the actually code. You can branch in different places. You can label codes. Labels are just addresses inside the instruction memory. So you can jump around. You can use, for example, branch equal. We call these type of instructions branch instructions. Before that, we also talk about load and store. Load is also considered immediate type because it's exactly similar. So load instruction is in a category of immediate type. But a store double word, for example, or a store long, um, uh, that's S type, a store type. And the branch is B type. So we have branch equal, we have branch not equal, we have also branch lower than or branch greater or equal. So these instructions are for changing the control flow inside the program assembly code. So yeah, we learned these codes. We also talk about jump instruction very briefly. J-type. We talked one instruction like jump and link. That's actually one of the instructions that we need for procedure call. When you want to call a procedure, you can use jump and link. The part of link coming from saving the address. Address is always in program counter. We need to save that to can come back. So that's a link part coming from that, jump and link. Also, we're going to learn today another instruction that's called jump and link return, that after finishing the procedure, you need to come back to the place that you were before without any problem to run the previous code without any issues. So we need to use jump and load return. We're going to talk about them. So today we're going to talk mostly about this issue of this part of the assembly that is procedure call. We need to see what is procedure and what is call. In high-level languages, you had them. As I said, procedure call is a like complex part in assembly language, but we're gonna put enough time on that, and we're gonna learn as much as we need. And to learn that, we also need to learn stack. Stack is a part of the memory. You know, when you are dealing with processor and assembly, sometimes you need some actually storage that you can't fit that in register. Register is very limited. In that case, you need to use memory. You have different type of memory that you can access. Like, for example, we have heap. Heap is a dynamic memory. When you use, for example, C++, when you malloc memory allocate. Malloc is an instruction that's using heap. And also you can use a stack. A stack and heap are actually two parts of the memory. If you want to divide the memory structure is like that. In computer, you have some, this is the virtual memory. Virtual memory that allocated to one process, not processor, process. Not this operating system give this memory. It's a virtual, it's not real. And most of the time that's, for example, 258 gigabytes, lots of memory. You don't have this much memory, but virtually operating system give you this range of address that you can use. In this range, you have some part that is actually you're not allowed to use them. At the beginning, this part is reserved memory. And then you have some part regarding to your code that we call it text memory or instruction memory. And then you have some part for static data. Static data is a data that is not changing. It's not dynamic, static data. And then after that is a dynamic part. That we call it heap. That start from low to high. And a stack is vice versa. A stack is from the highest part of memory down. So a stack pointer point to this part of the memory. The highest part of virtual memory, this is virtual memory, okay? So a stack pointer to is from top to down, and here text part or instruction can be marked with program counter. So in this picture, you can see 2 pointers to this memory, program counter and a stack pointer. A stack pointer specifies at the highest part of the memory, as you can see, is when you want to put something inside the stack, you need to decrease this stack pointer. Is vice versa, because the stack need to be like that. So because first in, last out. That's the structure of the stack in most of computers, including RISC-V structure, architecture. The things that you put first, you take it last. First in, last out. Okay, so that's some information that we need to know. Still, we're going to explain that more when we go to a stack part. I just wanted to let you know what we are dealing with in these following sessions. So yeah, we work with a stack. Why we need to work with the stack? Sometimes we need more than registers. We have very limited number of registers in this structure. Just 32 registers, not enough. Sometimes you need to save them somewhere to don't destroy them, especially when you are calling another function, because that function gonna replace those registers, gonna use them and destroy them. So you need to save them, especially when you have multiple functions that call each other, like a recursive functions, for example. Or you have, for example, a structure, you have a function that call another function, and that function call 2 more functions. You make a tree structure that the main function using all of these functions make a tree structure. So these leaf functions, we actually call them leaf functions. They don't call anybody else. They don't call any other functions or procedures. So this called leaf, this called non-leaf. We're going to see them today as well. Okay, so let's get started. To know all of this stuff, we need to first know what is the basic block. When we are dealing with coding, we always need to consider a piece of instructions or sequence of instructions that we call them basic block. Basic block is a sequence of instructions that just has one single entry point, that is the top, and one exit point. So it means there is no branch or jump between. You just have one entrance and one exit. This part is important for a compiler's point of view, because it can do optimization in that part. So let's see how. So this is called basic block. So basic block is a sequence of instructions, no branches inside, except at the end, and no branch targets inside, except at the beginning. So that's a definition of that. So anybody can guess why this is important for compiler to divide the code to the basic blocks. How compiler can use that? How compiler can take advantage of this basic block to make better optimized code? What compiler doing in general? Compiler changing the high-level language to the assembly language. So why, if there is no jump in this between, compiler can do better optimization? What optimization means? Optimization means to break this part to the lowest instructions, to lowest assembly instructions, to do faster. Yes?
Does it not need to use the memory if there's no branches or jumps? Can it just do it all with registers?
So they can use memory inside. There is not just branch and jump inside. So there is no change of control flow. Any other idea why compiler? Yes? Yeah, that's exactly. It's regular. It's like sequential. You're not changing that. First of all, the pipeline working very fine over there. And when there is no jump between, compiler allowed to replace instructions. Check, for example, some instructions maybe are extra, just remove them and replace instructions, combine instructions and play with this part, because there is no jump here. Everything here is sequential. This after this, this after this. So this is sequential. So compiler allowed to play with that, to do it as optimized as possible. Sometimes remove some instructions that we call them redundant instructions. Sometimes combine instructions and even reorder instructions. For example, realize, okay, if I put these two instructions instead of here, it's gonna run faster. Why? Because of pipeline. Pipeline is sometimes need some instructions be far from each other. Like, for example, load. If there is two load and store close to each other, is not good. You need to put, for example, one register between. We can see that. Or sometimes if there is other things, we can actually like unroll things, to make that part faster. So in general, this is basic block. Basic block is control always enter and control always leave at the last instruction. And compiler using that for optimization. So how I can explain here, for example, compiler can remove redundant instructions, can combine instructions, can reorder instructions, or eliminate some dead codes. Dead codes are the codes that you just by mistake put there. Eliminate dead code. Okay, so in these ways, compiler can do better optimization in basic blocks. Also, basic blocks are like a foundation of procedure call as well. Okay, let's see more about procedure call. Okay, first we need to see what is procedure. Any definition, anybody can tell me what is procedure? Yes? Function. Yeah, that's another name. What is function? That's another name for procedure. Function, procedure. Sometimes, I don't know if you know, for example, Java, in Java called what? Do you know Java? Called method. In Java called method. In some other languages, maybe called subroutine. So they are all the same. Procedure, in some old languages called procedure. I remember Pascal, what was another programming language that I learned when I was a student, undergrad. We had very structured, very structured language was called Pascal, and in that Pascal, we called functions procedure. But in C++, it's called function. Okay, so yeah. So what is that? What is definition of function? Yes? So the set of instructions that has input and output?
Yeah.
Okay. it not
Well,
the
sometimes.
okay. So any other? Yeah, that should be any other definition for function. Like for example, you are defining a function called sum that adding two numbers. What is specific about that part that adding these two? You're you're doing something with that, and you can repeat it as much as you don't need to repeat it again. You just define it one time and call it multiple times. So the function is like a block of code that you're doing a task, but reuse it many times. That's the that's a, and this kind of programming language called actually functional language or procedure language, because you can define a procedure and call it many times. Is make a structure makes a structure for language. So uh, normally procedure is um, a block of code that perform a task but can be reusable. That's the part that is important. Reusable. Okay. What about calling? So with procedure, you define a procedure. Okay, but let's do example. Like for example, you can have a function called sum. Let's change the color. Sum that get two parameters like a and b, and okay. So for example, let's make it um, int. For example, int integer, and the output is integer too. And inside we return a plus b. So this is the C structure. So you have a function called sum that is adding two arguments, a and b, or parameters, add them together and return them back. We consider here integer, but it can be double integer or long integer. That integer is 16 bits in C. Long integer is 32, and long integer is 64. Because in this processor that we are working is 64, registers are 64. If we want to implement that function, instead of integer, we need to put long to make it more easy. Okay, anyway, that's a function. And calling, what is calling? Calling, we need to call that function somewhere else. So for example, in main function, you call this. How you call this? You just write, for example, x is equal to sum, and the values that you want to send to that procedure, like 3 and 4. So this is how to call that procedure. So you define a procedure called sum, and you call it. So this is calling. Okay, so we want to implement this using assembly language, low-level language. Let's see how we can deal with that. Sometimes this procedure is so simple, like this, doesn't have that much things. You don't need to use a stack for that. You just need to send parameters somewhere to can use it. I mean, here you need to put a parameter somewhere to can use it over there. And you have, when you call it, you need to return back exactly the same place. Okay, so okay, just consider this example. Okay, I just clean this up. When we are dealing with procedure call, you need to have two definitions: caller and callee. Caller is actually flow of a set of instructions, or it can be another function too, that actually call that new procedure, and the new procedure called callee. So so that's a definition that we have. Caller is actually the code that's called procedure, and a callee is that procedure. Okay, and after finishing, you need to come back exactly to the same flow that we were before. So when we call callee, when caller call callee, it need to send parameters, and when a callee finish its job, return the values result. So return results. So the results coming back to caller. We want to see how we can manage this in low-level language. In RISC-V, the machine that we are working on, or the structure architecture that we are working, so it's using like conventional method for procedure call that need these steps: passing arguments, we're always dealing with arguments, and transfer control. So instead of fetching from here, we start fetching from here. That's the transferring control. And managing a storage. If we want here, for example, work with some registers, we need to save the registers and use them and return them back. That's called managing a storage and returning result back. So this is in very high level. We're going to go very lower level, step by step. We're going to see how we can deal with procedure calling. So that's a let's do one question. This is an iClicker question. I want to see. So we are asking, let I go and define that. Let's see. Okay. Start class. Cool. Okay, good. Okay, so I'm asking here, try to do that. We have a procedure, we have a function, and which of the following actions is essential to ensure correct return to be to the caller? Return to the caller. That's the important part. How we can correctly return back. So which one is the correct? Saving the return address before jumping, allocating a space for local variables, and the heap. Right now, you know what is heap, and storing all registers are used by the procedure automatically is not automatically, and flushing this instruction pipeline that's not related. So which one is the best answer? Let's see what is your result. Yes, one is the correct answer. That's correct. Saving the return address before jumping to procedures. That's the main thing that we need to consider, because we want to correctly return back to the caller. So how we do that? We need to save the address that we were before. We need to kind of saving returning address. We know in RISC-V we have a register for that called X1. X1 is a register just for return. So we always put that. What is just one register? So if we have multiple functions that calling recursively each other, we have problem. Can you imagine how we can solve this problem if we have like nested call, but we have just one x1? How we solve it, how we deal with this problem? Nested call. Do you know what do you mean what I mean by nested call. So you have this function calling another function, and this function, without finishing, call another function, and we just have one x1. So when we save this one as a x1, this one also wants to save the return address inside x1. So it's going to replace. So how we fix it? Any idea? Yes?
Do you want to use the stack?
Yeah, perfect. Yeah, we use memory. Anytime we have problem with register, we use a stack or memory. Memory is okay. We have a long memory. Even though our registers are limited, memory is big. That's correct. Very good. Okay, so let's go to close this. Okay. Yeah, we can use memory, of course. So the one is the first, the correct answer for this example. Okay, let's see in details, in a very general way, how we deal with procedure call. The first step is to, okay, let's see what is the problem first. So we have a function, like this function. We have long sum. Maybe I just put L. L means long. Okay, long A, long B. So this is a function, and we return A plus B. Okay, so this is the C function for summing two 64. Long means long 64 bits. We are using long as a data type for this C code, and we have we want to call it again long somewhere else. We call it sum 3 and 4. Okay, let's see how we can write this using RISC-V. First step is to place parameters in registers. So we have some specific registers from X10 to X17. This set of registers called actually argument registers. The X10 and X11 mostly used for return, but all of them in general called argument registers. Okay, the first step is this. For this example, what code we need to write to actually put argument inside X10 to X17. Okay, so we can use load instructions, but we don't have load instructions. We kind of have in assembly. We have, I think I explained, or maybe not. We have some instructions called pseudo instruction. Pseudo instructions like load not exist in the hardware, but exist in assembler. Anytime you use pseudo instructions, assembler gonna change it to one real instruction. You know, load immediate not exist, but you can implement that using add immediate. Add immediate with x0 is like load. So that's why this kind of instruction is called pseudo instructions. Pseudo instructions are not exist in the hardware, but exist in assembler. Assembler replace them with other instructions. We have couple of instructions that consider pseudo instructions. So, okay, so this is one of them. So we put 5 in x10 as a one argument. Oh, actually it's 3, it's not 5. 3. And 4 is another argument we put in x11 again. So that's for the first part. Let's call this 1. 1. Second step is to call the procedure. Okay, the procedure called sum. We need to call it. How we call it? We have a jump instruction, jump and link, x1 and sum. x1 is the return address. So x1 is return address. So let's write it up. Return address. When you run this code, it's jumping to sum, but put program counter +4 in x1 that we can come back later. Okay, that's how it works. Okay, so to call the procedure, we need to use this instruction, jump and link. Okay, that's done too. What's the next step? The next step is actually we need this step if our procedure is a nested procedure. In this example, we don't need that. We're going to pass about it. We don't need to save x1. But if our procedure is going to call another procedure, we need to save x1 in the stack as well. Okay, let's consider this nested. In this example, it's not nested, but let's consider it's nested. It still works. You know, that this procedure, these steps, doesn't matter your procedure is nested or not, for both case works, okay? But you need to write more code. Okay, let's try to save x1 in the stack or at the stack. Okay, so let's see what we need to do. First of all, why we need to do that? Because x1 always contain the return address. If the procedure call another procedure, so that's gonna overwrite x1. So we need to kind of save it in a memory. So how we do that? To use with the stack, this is a step 2, step 2, step 3. First, we need to use a stack pointer. Again, assembler knows a stack pointer, but it's one of the registers. I don't remember that right now, but normally you need to because a stack is from top to down, you need to add integer, a stack pointer -8. It means you need to go, why -8? Because a stack pointer is 60, like each register is 64, so 8 bytes. So if here was a stack pointer, we go down. Each of these is 8 bytes, okay? So we move a stack pointer down. Now we can save, we can store x1 in the stack with this instruction. Okay, I'm going to explain it again here. So this is how we are working with the stack. What we want to put in the stack, x1. What is x1? Return address. Okay, return address after this jump is going there. So we need to save it kind of. In this example, we didn't, we not, don't need to do that, but we want to do these steps. Doesn't matter. We save it and return it back. Okay, so what we do, we change this stack pointer to down, because the stack pointer is the reverse. It's not going from 0 to up, from up to down. So we actually do a stack pointer -8 and put it again in a stack pointer. We are going down. And then we put x1 here. So whatever stack pointer was there, we don't need that anymore. We have a new stack pointer. And inside this is a return address. Okay, that's how we deal with a stack pointer. That's a step 3. Okay, so that's a step 3. Let's see what is a step 4. A step 4 is to allocate a storage for the procedure. Okay, maybe in this procedure, because it's so simple, we are not allocating any memory. But if we want to allocate memory, like for example, some load, instead of just add, we had some complex instructions. We need more memory for those instructions. Again, we need to put some space here for those memories. So imagine we just put some space for that. Like how much? Let's consider, for example, 32 byte. So if we want that, again, we add I, a stack pointer minus 32. This is just for a storage. This is not necessary for this code, but in general, we need that. So this is a step 4. Okay, step 5 is to perform the procedure operations. In this example, it's just add. So I'm just going to write it here. 5, step 5 is just add x. So we have in x10 and x11, we add them together. 10 and 11, and put them in 10. Okay, so this is the normal operation that we need. Step 6 is to place result in x10, because x10 is return registers. So it's already there. We don't need to do anything for that. Step 7, restore x1. If we save x1 in the stack, we need to restore it. We did in this case. So we need to restore it. How restore it? We just do actually load. Easy. So we load from a stack pointer to x1, because x1 is always return address, and change the stack pointer to previous address that it was. So a stack pointer, we added by 8 and return it back to a stack pointer. That's it. The last instruction is return 8. I don't know, this part of my screen is not writing 8. Okay, so at the 8 is jump, and so this is 7. Jump and return x0, x1, 8. Okay, I'm going to explain. So that's another instruction, jump and load return. We call with jump and load. We return with jump and load return. So it's doing same in jump and load, put them in x1, in here from x1, we are jumping to x1. What was x1? Program counter plus 4. Program counter plus 4. With wherever we were, we added by 4 because instructions are 4 bytes to go to the next instructions. And we jump there. That's it. That's how we call instructions. If you didn't get all the point, that's okay. We're going to go step by step in next slides. Oh, the time is over. Okay, next class. We're going to talk about this example was one of the examples that had all the cases. Okay, any questions? But if you didn't get that, no worry. We're going to explain it a lot more next time. Okay, so see you Friday.
Lab 2, yeah, that's what I'm working on basically all day today. I just finished it like in data structures. But I kind of